Well, hello and welcome YouTube. I'm watching the pitch while I'm trying to record. Hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Okay, step on inside, and we are on section 1.6 of Big Ideas Math Integrated Math 2, the end of the chapter, I suppose, on exponential functions. Now this one seems to be longer when it comes to the fact that we may have to graph some things. There are 70, it might be 76, 74, something like that, problems, and just in that nature. We might have to use the calculator here and there. I haven't really seen them a great deal, so let's go ahead and see what we have in store for us in the lecture portion of this to begin with. Okay, so graphing exponential functions. Here's some of the core vocabulary. A lot of big things. I see recursive rule. Okay, I didn't know we were going to do that. Geometric sequences then? I don't see that on here. Okay, graph exponential growth and decay functions, write exponential models and recursive rules. I guess we're going geometric sequence. And rewrite exponential functions. So maybe based on how it's set up, we have to do something like that. Okay, an exponential function has the form y equals ab to the x. That is a times b to the x. A can't equal 0, otherwise it makes it a constant function. And you can have a, I don't see the other word here. You can have a function grow or decay. It can grow or it can decay, and you're going to see different forms of graphs there. I see a growth function, and b is known as the growth factor. Now there are different ways that a affects the graph, different ways that b affects the graph, and we're going to be able to see them just fine. Now here's my guess, and I'm not certain on this, but on the absolute value section, graphing absolute values, the book does a lot of let's make a table. Let's do that. I'm not big on the table usage of these graphs, as in making a table to plot the points. You'll see different ways that I go about doing that, featuring what is known as the asymptote. Here's that word, featuring what is known as the asymptote on the graph, and things like that, things of that nature. So I might use their tables in their examples to explain how I'm going to be doing it without it. Actually, this might kind of help a little bit, and this might be all that they ask you to do to graph. In a parent function, f of x equals b to the x, where b is greater than 1, you have a graph that ends up growing and taking off this direction. Now notice that a isn't here. That's because the a value is actually just 1 in this case, and where the a affects your graph is, in this case, the y-intercept. That ends up being the a value for these graphs that don't have any transformations, no h, no k, because when x is 0, b to the 0 is 1. That's something that we learned the other day. And then f of 0 is 1. That's exactly what you get here. As x increases, as we know from exponents, as x increases, you keep multiplying another b as you go along, and that's going to affect your y. So as you go over 1 by x, there's another b multiplied to your graph. So check this out. From 0, 1 to 1b, what happens is x increases from 0 to 1, y increases from 1 to b. You multiplied 1 by b. After that, x goes to 2, you multiply by b again, and you get b squared. So whatever your b value ends up being is what happens. And if b is greater than 1, then it's going to take off and grow as a result. I'm sure we're going to learn in, oh, yep, here it is. We're going to also figure out exponential decay, which is when b is not negative, but a value between 0 and 1, let's say 1/2, because when you multiply by 1/2 over and over, your value shrinks in this decay-like fashion. So if you look at this graph, same idea. A is 1, and now b is, let's say, 1/2, or so, a fraction less than 1. Now you keep multiplying by that b value, that fraction, and your value shrinks more and more and gets closer to 0. The idea here is that it gets closer to 0 and doesn't actually hit 0. What happens when you take half of a 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 half? It never hits 0. It never becomes negative, just a very small number, almost in a might as well be 0 kind of way. And I don't know if they pointed this out the first time, but the x-axis is known as the asymptote of the graph. An asymptote is in our case, that we're going to be drawing, let's make it bright, a dotted line. It's not part of the points on the graph itself, but it helps describe how your points are possibly approaching something on a graph. This dotted line right here is showing these points take that half of a half of a half over and over and over, and we're getting closer to 0, and visually it might look like it's actually intersecting with the black, but this orange line can then tell us, wait, I'm trying to redo, this orange line can help tell us that no, it actually isn't. It's approaching it and never actually touches or crosses it. And that's just the end behavior of the graph. That's just what it's doing. Now on the other side, it's taking off in that direction because we're dividing by, say, a half, which is like multiplying by 2. So that's the nature of your graphs. They will either take off away from an asymptote like that, they'll get closer to an asymptote like that, both above the asymptote, or you're going to see some that go down below. And I believe that that's what's coming next, because you saw ones where a was greater than 0, where a was 1. Okay, they don't show any negative ones here, and I don't know if they're actually going to do any. But if a was a negative number, then they'll be below the asymptote, so we'll see those. All right, so here are some examples. 2 to the x and 1/2 to the x power. Like I said, using those as general defaults is good. So take a look at this table and what's happening. What happens when you do 2 to these powers? 2 to the 0 power is 1. That's where you have the y-intercept. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the negative first is 1 over 2 to the first, 1/2. 2 to the negative second is 1 over 2 squared, which is 1/4. When you plot them on the graph, it has this behavior. But, as you might be able to understand, because this is how I'm going to do it, I'm going to start from my a value, which will end up being the y-intercept. When x is 0, all you have left is a. So I'll be starting at, in this case, 0, 1. And then as x increases by 1, you double your previous distance from the asymptote here. From 1 times 2 is 2, times 2 is 4, times 2 is 8, and you see that jump right here, times 2, times 2, times 2. Going this direction, we end up dividing by 2, half of 1 and half of a half. Dividing by 2 is multiplying by 1/2. So you're going to see those instances from me, and I can do it very quickly, and you'll be able to as well without use or need of a table. Same thing from the 1/2 version. Take a look on this side. 1/2 to the 0 power is 1. 1/2 to the first is 1/2. 1/2 squared is a quarter. And the other side, you end up flipping the fraction, and you basically just get the opposite effect of what we just saw. So now, when I start from my y-intercept as basically a reference point, the a value, I will take half of 1, which is a half, half of a half, which is a quarter, and then multiply by 2 going this direction. So you're going to see versions of that. I assume that when we get to do these graphs, and I'll be providing that graph paper in the description section when we do these. Okay, writing exponential models and recursive rules. I was actually caught by surprise seeing that recursive rules are here. Well, these aren't recursive, these are exponential models. So an exponential growth and decay model can be provided from these here. Now, I wrote on the previous video in a version of interest rate increase, and it looked like, I think we used the letter f. F equals p times 1 plus r to the n power. This here very much mimics this here, so much so that they might as well be the same thing. I mean, they are. You're just switching around some variables. N is t, p is a, f is y. But they are the same thing. And the process within here is that if r represents some growth or decay percentage, you determine that with a plus or minus, and you convert that percentage to a decimal. We add or subtract from 1 because 1 represents 100% of our value. So if I want a 20% increase of something, I add 20% to 100% to make it a 120% increase. If I want to take 20% off of something, I'm left with 80% because I do 100% minus 20%. The reason is it's a 1 is because it's the decimal equivalent of that percentage. A ends up being the initial value, kind of like your y-intercept in some ways, or p the principal amount, and y is the final amount. So you can get a final amount of something, growth or decay. It doesn't have to be money. It can be population. That's another very popular one. There are a bunch of other things, and we'll see what we run into, but these are the models we're going to use. If you ever see me write it, sometimes you'll see me write it with a plus or minus and say you determine which one it is based on growth or decay. And t does not have to be in years. T can be in days. If it's 2% growth every day, that's just what it is. Okay, so here's an example of an exponential model. Population of a country was 6.09 million. That's going to represent your a value. You can see a is 6.09 on this date. So this is like your time 0, and then we're going to see how far they want to go from there. 1.18% increase is going to be your r value. The increase means we'll be using a plus, and the r value, we have to shift the 2 decimal places over to get 0.0118 in that case. And then we write a model first. Now the model basically still has t in it because we haven't yet answered a question based on that. So this would be the model of it. And then they ask, estimate when the population was 7 million. Oh, in fact, we're not substituting for t at all. Well, we sort of are. They said estimate. When was it 7 million? Now we have to substitute 7 for y because the y is in millions here. And we have to figure out what t value gets you there. So I guess you're basically, we're not solving this algebraically because you haven't yet learned what are logarithms, so I guess you're substituting values for t, and we have to do that together. It's basically a guess and check, and it looks like they might even end up using a table in the calculator to do that. I'm not going to show you that because we have different calculators, but it's possible to do. Apparently, wait a minute, where's the question? Estimate when the population was 7 million. I don't see when they show... Oh, use the table feature. Okay, so around 11.9. It looks like they plugged in 7.5 as a guess and check. Oh, 7.5 was 6.65 million. That's not enough yet. You keep substituting numbers, and when you hit around 11.9, then you get about 7. Y equals 7, 7 million. And 11.9, remember, this is years since January 1st, 2000, so that ends up being 11.9 years after, near the end of 2011, around 2012. So it's a word problem, you answer that way. Recursive rule, this is one, I don't know how deep I want to get into the idea. Well, I guess I have to a little bit. First of all, okay, they're using function notation, not subscript notation, and they use f of 0 instead of a sub 1, okay, or instead of f of 1. So a recursive rule is basically a way that says, I mean, they say it right here, it tells how a value f of n is related to a preceding value f of n minus 1. Recursion is the act of getting something from the thing before it. So when you look at that previous table that we had right here, if I asked you what's the growth pattern of y, people would say times 2. They say times 2 times 2 times 2. That's what's known as recursion. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. You get the next term based off the previous term. Not all math does that. We barely ever do that, in fact. You know this t? We didn't plug in 1... we didn't multiply by this number here and then do it again and again and again until we hit 11.9. We plugged in numbers. So that's more of what's known as an explicit rule. So recursive rule is a little different, getting the next value from the previous. And you can write exponential models that way if you want to. You start from some governed initial value, this upfront, let's see if they say that here, initial. You start from some initial value we're going to call f of 0. They give it to you, or we use it based off the model. And then r represents that growth rate, how much you're multiplying by to get to the next value. And that's what they're saying here. If you want to define f of 1, you take f of 1 minus 1, f of 0, and multiply by r. Boom, you get it. To get f of 2, take f of 1 and multiply by r. To get f of 20, you take f of 19 and multiply by r. So you find the one before it to get it. So here's their example. 6 times 3 to the x power, where this is your a, kind of your y-intercept, your initial, ends up being this f of 0. And then 3 is what you multiply by each time. So the rule is this, and I know it looks weird, but if I want to find the next value, if I want to find f of 1, I'm going to take 3 times f of 0, which is 6. 3 times 6 is 18. And then I'll do 3 times 18, which is 54. 3 times 54, which is 162. And you keep getting other values. Okay, so examples of recursive rule, we see it here once again. Oh, is that word problem? So they're going to do that same thing. Remember, this is your r value, multiplied by the previous term, and we start from 6.09. Perfect. I don't see any examples of graphing with negative exponential growth or decay, so it seems like we're not doing that. And that's fine, because we want to deal with word problems that have more context in the positive form, even if it's decay. Next, we're going to look at rewriting exponential functions. And exponential functions can have exponential growth or decay, and we know that's determined by whether b is greater than 1 or between 0 and 1. But that is when you are in y equals ab to the x power, meaning x or t or whatever it is the only thing in existence in the exponent. But if it's not the only thing in existence, such as this t over 4 or this t minus 3, then it's possible that we're looking at a different form of something. Because now when x or t increases by 1, we don't multiply by 0.96. You have to get t up to 4 to do that, because it takes every one integer, successive integer, over to have another multiple of this. So what we're going to do instead is rewrite these equations so that there's just a t up there. And we should be able to have some form of it based on our exponential properties. The sections leading up to this are built for us to be able to use this one here. So in this first example, you have this function, and if you want to get the true t here, you extract t out from here. This is t times a quarter, And we know that power of a power property has exponents multiply when you have 1 raised to the other. So let's bring the t times 1/4, or 1/4 times t, and bring the 1/4 in with the 0.96 and make it raised to the t power, and then evaluate this. And I'm sure this is rounded to 0.99, but you can see its true value isn't actually 0.96 every t times, it's 0.99. And now you know specifically what this is in this form. It appears to still be decay, but not as largely as it was before. And then you can identify what r is from that. This next example, t minus 3 in the exponent, remember subtraction of exponents comes from the division of something and something else with the same base. So 1.1 to the t over 1.1 cubed, and you can see that very rewrite of this here. Now there was no a value in front of here, which means a is 1. But if you rewrite it as this, then this can also be rewritten. Let me write this as 1 over 1.1 cubed times 1.1 to the t power. So the bottom is kind of written out in front as the a. And I guess through their calculation that this turns into 0.75. I guess that's the idea. So what looked like was 1.1 exponential growth actually didn't end up being it at all. It ended up being, oh no, I take it back. It's still growth. It's still growth. But the y-intercept is no longer 1 because of this being a horizontal shift. And we're not graphing as a shift together, but this would be shifted 3 units to the right. So if we shifted 3 units to the left, the a value is now different as 0.75. But the 1.1 is still as is. So we'll see different examples. Here are some that they show, but of course we're going to do our own problems together. And more to do. Let's see how far we've talked so far. 16 minutes in just a lecture. Solving a real life problem. Let's see. I'm probably not going to do the entire thing here. Okay, we've done some word problems. The thing I want to make mention of, I thought we just did this. Maybe they told us the numbers straight up. If something loses 12% every year, that's your R value, and it's a loss. That's why they subtract these values here from the initial. And then you end up getting a model. I thought we just did these sort of. So I think I'll leave these be. They show something about graphing the model, which is nice. That's why you want the model with t still involved in it. I'm fine with that. I'm just going to go ahead and move forward. We spent a lot of time with this, and I want to get to what we started with initially, which was probably graphing. So I want us to get prepared for that. Oh, there are a couple problems before that, actually, some vocab check. Let's start with those. And then like 70-ish problems we go. This is going to be a long one. Vocabulary. In the exponential growth model, y equals 2.4 times 1.5 to the x power. Identify the initial amount. That'll be 2.4, because when x equals 0, this part goes away. The growth factor, that is 1.5. That's what you multiply by each time you go. And the percent increase. Now, the percent increase comes from, you know how that whole thing was like 1 plus or minus r? Well, 1.5 comes from 1 plus 0.5. That means r is 0.5, which means it's a 50% increase. Your percentage increase or decrease is 2 decimal places over from, to the right, from your r value, and that's what this thing is. It's a 50% increase. So 2.4 initial, 1.5 growth factor, which makes it grow 50% from the previous value. Which one doesn't belong? Which characteristic of an exponential decay function does not belong with the other three? Explain your reasoning. Okay, we're going to begin with a base of 0.8. The base is like from 0.8 to the x power, like that. So I don't know what else is coming. Decay factor of 0.8. Yeah, that I'd say that belongs. I want to make sure to not confuse it with decrease, like this right here. 80% decrease is something different. I'll talk about in a second. Decay rate of, oh, hold on a second. Let me think about that now. Because it says does not belong with the other three. I want to be careful with how I say this. Okay, yeah, decay rate is 20%. Okay, that's fine. Decay rate of 20% also belongs, and 80% decrease does not. Okay, so there's a difference between decay factor and decay rate. Decay factor is the value that you're specifically multiplying by. Decay rate is how much is being removed from your 100% amount. That's why 80% decrease, that also means the same thing. How much you remove from the 100% amount. So I shouldn't even underline those things as the same. These two mean the same thing, but these are two different numbers. So when you remove 20% from 100%, that is 80%, or 0.8 as a multiplier. Decay factor of 0.8 is literally the same thing, base of and decay factor, so I should underline those. Those are the same. And a decrease is like a decay rate, how much you take off from the 100%, so that's different. Okay, so that's kind of a long conversation, but actually that was really important for you to see, because if they have those words, we have to make sure to do those. And I'm sure a calculator will be in play at some point with exponential functions, so I have mine ready. Get yours ready. We are going to be able to go ahead and start with problem number 3, and let's see what we are dealing with here. Okay, in exercises 3 through 8, evaluate the expression for x equals -2 and x equals 3. So it looks like in these first ones, we're literally just substituting. So we want to find out what 2 to the -2 power is. That's 1 over 2 squared, which is 1/4. And then 2 to the 3rd power is 2 to the 8th. Now, whoops, is 8. Now, I'll be honest, this is great review for some of the exponential property things that we were doing in the past, but because I won't be using a table in particular, a lot of this won't be relevant to what we do, except for remembering that anything to the 0 power is 1, and we're not raising these to the 0 power. Excuse me. Number 4. 4 to the -2nd power is 1 over 4 squared. I won't be writing that each time unless something's way different, which is 1 over 16. And then 4 cubed is 64. Number 5, 8 times 3 to the x power. I think it's a good time to stress the importance of order of operations and remind everybody that I can't multiply 8 with 3 to get 24. Much like whenever you have a function that looks like that too, I can't multiply those first. The exponent goes first. So in this situation, let's do 8 times 3 to the -3rd power. In that same vein, as far as order of operations goes, the 8 doesn't go down with the 3, excuse me, to the -2nd power. To the -2nd power. The 8 doesn't go down with this as well. It's just the 3 that goes down there. So this becomes 8 times 1/9, or 8/9. And by the way, unless I'm dealing with a word problem, you'll see me more than likely on a graph say things in fraction form, I think. Depends on what kinds of numbers they give. Unless they give me something in decimal form, then maybe we have to stick with it. 8 times, 3 cubed now is going to be 8 times 27, which is, I should know, 216. Yeah, 216. All right, number 6. 6 times 2 to the x power. Let's kind of save ourselves the workload of what we're writing and go straight into it. Whoops. I think I'm feeling the effects of this is going to be a long video, so we'll see. All right, 6 times 2 to the -2nd power. 6 over 4. 1 over 2 squared, which is 3/2. Let's reduce that. 6 times 2 cubed is 6 times 8, which is 48. It's interesting that they ask us to substitute -2 first. It seems like the harder problem to do, and normally wouldn't you want to do the less hard problem first? I don't know. Maybe they're assuming that when you use a table, see, even if I did use a table, I'd start at like 1, 2, and 3, or maybe whatever, 0. I wouldn't start at the negatives. All right, number 7. I have 5 plus 3 to the x power, or 5 plus 3 to the -2nd power. I was going to say what makes these different. Now I realize I have a fraction, which makes it harder. 5 plus 1/9. You could say 5 1/9, but I'm an improper fraction guy, so 45/9 plus 1/9, which is 46/9. And when I say I'm an improper fraction guy, I mean I think all math teachers are improper fraction guys. They're okay with it. They're comfortable with it. They prefer it. That'd be a repeating decimal. We don't say mixed numbers really anymore. Unless we're plotting it on a graph, which might be relevant to this. 5 plus 3 cubed is 5 plus 27, which is 32. These were part A and B. I really should have been putting A and B on all of these. My apologies. I didn't notice that. And number 8, 2 to the x minus 2, kind of the same thing. Going back to my happy blue. 2 to the -3rd power minus 2, part A, is going to be 1/8 minus 2. 2 is also 16/8, so 1/8 minus 16/8 is -15/8. That'll work. Part B, 2. Oh, I'm sorry, it's not to the -3rd. I don't know why I keep doing that. Let's do that one more time. -2nd. At least you saw one. All right, 1/4 minus 2, which is 1/4 minus 4/4, which is negative 3/4. And 2 cubed minus 2 is 8 minus 2, which is 6. Apologies. Okay. Okay, let's move forward. Determine on these ones whether the function represents exponential growth or exponential decay, then graph the function. So, let's go ahead and do this. Number 9. Y equals 6 to the x power. Now, for the sake of all of these being y equals ab to the x power, I do want to point out that the a value in this case is 1. And that's important for my graphing thing because I'm not going to use a table, and I want to also show where the asymptote and stuff goes on it. So, because, let's see, they say exponential growth or decay. Now, first of all these are positive exponential growth or decay because a will always be a positive value if you look at all the problems. Actually, a is 1 on all of these, so it's always positive. But growth versus decay, because b is 6, that's going to be growth. As long as it's more than 1, it's growth. By the way, b can never be 1 or 0 because you multiply by either of those, it either stays the same or it is always 0. And it can't be negative for a lot of other reasons, unless we're talking about geometric sequences, which we sort of look at with recursion, but not fully. You're not going to be looking at negative b values. So it's either going to be between 0 and 1 or greater than 1, and this one's growth. So exponential growth, and then we graph. So my graphs will look like this. The y-intercept, when x is 0, 6 to the 0 is 1, times 1 is 1. All of these y-intercepts will be at 0, 1 for our benefit, I suppose. Maybe later, we'll see something different. The b, when x increases by 1, we multiply by 6. 1 times 6 is 6. You increase x by 1 again, you would do 6 times 6, which is 36. We can't fit that. So we're not going up 6 or even up 5 over 1. We are in fact, let me say this. You're not going up 6 from 1. You're going up 6 from 0, from the asymptote. It's 6 times larger, not 6 farther away. So I want to make sure you note that difference. That's pretty important. And as you go to the left, you would divide by 6. If I took a sixth of that, that's literally 1/6. And I can't really do much more than that, so that'll be my graph. The slowest part for me will be drawing the curve, but in the future, because I have a bunch of these, you are going to hear me go a lot faster on getting those points, especially because we did it a little bit in lecture. This is one of them, and the a isn't changing, so there's not much more to talk about. Now, this asymptote is a feature for us to kind of state that, well, it's not going to cross that. And if you do notice, I am drawing a full arrow here, and I draw a half arrow here. I don't know if other teachers draw half arrows. I don't know if this was self-taught or if this was learned from somebody else. It's just my way of saying that it continues forever in that direction domain-wise. But and the range is technically, it's going down forever, but the range is limited because it stays above 0. So my half arrow is a way of saying it's going down closer and closer to the asymptote, but never touches or crosses, whereas this goes forever right and forever up. So that's for future reference. Number 10. Y equals 7 to the x power. Now 7 to the x power and 6 to the x power ain't very different. In fact, you're probably going to see the odds on one part, like 9 and 10 are going to be kind of the same, 11 and 12 kind of going to be the same. That's probably what's going to happen here. So this is once again exponential growth because b is more than 1. The a value is 1, as it will be for all of these. And 1 times 7 is 7. And 7 times 7 is 49, which I can't fit. And 1 divided by 7 is 1/7, which looks a lot like the 1/6. So the only real difference between these two that you will visibly see is that there's a point that's 1,7 instead of 1,6. Otherwise, these look very similar. And that's really all I can fit. Hopefully there are other problems where we're going to be able to fit a little bit more. So we'll take a look when we're there. All right, number 11. Now we have y equals 1/6 the x power. Having this in parentheses is important. If you notice, 9 and 10 aren't in parentheses. Not that you can have it in parentheses. This is required because the property states that you want both the numerator and denominator raised to the power. So for your own sake, always try to put parentheses. It's one of those when in doubt things. Now, 1/6 is a number between 0 and 1. That makes this exponential decay. That means that as x increases, your y values get closer to the asymptote, closer to 0. The y-intercept is still 1, but now as you go, x increases by 1, you multiply by 1/6, which becomes 1 over 6, and then 1 over 36 and shrinks. And then you divide by 1/6 going to the left. 1 divided by 1/6 is 1 times 6, which is 6. And now you see basically a flipped version of number 9, where it reflects across the y-axis, and here's some positive exponential decay, getting closer and closer to the asymptote. There. That's all they're asking, right? I want to make sure they're not saying domain and range, which would be a nice thing to bring up at some point, but I don't think they even did in the lecture material. Number 12, y equals 1/8 to the x power. Very much, it's not 1/7, but very much like number 10, this is going to be not very different from number 11 with the exception of the appearance of one value. It is exponential decay. And we will take an 1/8, which looks like a 1/6 and a 1/7. We're taking an 1/8 of 1 that way, and we'll multiply by 8 this way. So that's the other part that you see. It takes off a little taller, even taller than 1/7 would. Now, I probably should be using, not that it would affect these graphs because it would still be too tall, I should probably be using a taller set of graph axes. In fact, let me do that right now. Let me pause this for one moment. Okay, I have resumed. You're going to see this on the next one because we're done with the problem, right? I think so. Okay. First of all, number 13. But also, I'm going to be using a taller set of graph axes now, looking like this. The reason being because I want to be able to fit some points that extend beyond 10 and -10 potentially. Not much. It looks like it only goes up to, here's 5, 10. There's no numbers, I'm sorry. 15 and 17. Hopefully you can see these little hashes. That'll be nice. See, the other problems aren't really affected because that 36 and 49 you still can't fit on here. But hopefully we can fit some other kinds of problems. So number 13 is y equals 4/3 to the x power. Now 4/3 is a fraction, but it's not a fraction less than 1. It's not 3/4. It's 4/3. That's 1 1/3. 1.3 repeating. That number's more than 1. That makes this exponential growth. And this is one where I'm going to be able to fit more points, and I want to try and do it in a very mathy, like improper fraction, whatever kind of way, which I can convert to mixed numbers. First I start with the y-intercept of 1. And then you multiply by 4/3, which is 1 1/3. But 4/3 times 4/3 is then 16/9, which is 1 7/9. So 1 7/9 is closer to 2 like that. And then, oh man, maybe I regret doing this now on this problem. 16/9 times 4/3 is 64/27, which is 2 and something, right? 2 and change. 2 and, what did I say? 50, sorry. 2 and 10/27, so about like that. So every time x increases by 1, I'm multiplying another 4/3. 64/27 times 4/3 is 256 over 81. I'm only going to do this for so long on this one this time, which is about 3. It's a little more than 3 and change. Multiply that, you get 1,024 over 243, which is a little more than 4, right? Because 250 would be 1/4 of 1,000, so a little bit more than 4. So you can see that growth take off. I'll do one more. I'll do 4,096. That's multiplying by 4 over 729. That's multiplying by 3, which is less than 6. So somewhere between 5 and 6, I'm sure. So let's say about right there. You can kind of see that take off, right? So it takes off there, multiplying by 4/3 each time. And I would keep going, but I decided finally maybe I shouldn't actually keep going there. You multiply by 4/3 going to the right. Now you divide by 4/3 going to the left. Dividing by 4/3 is the same thing as multiplying by 3/4. So you're taking 3/4 each time you go to the left. So 3/4 of 1 is 3/4. 3/4 of that is 9/16. That's a little more than a half. And you can see it kind of slowly converge this way. So this is a very pretty graph. I love the concept of it. I do wish that Maybe the y-intercept was a little taller, so I could actually stretch it to the end of the graph, because I'm not going to actually keep calculating that over and over. But you can see that. And they didn't tell us what to limit our points to. They probably go from -2 to 3, because that's what they were doing before. And yeah, that's good enough for me. It's actually quite pleasant. Okay, y equals 2/5 to the x power, number 14. Y equals 2. All right, this one is a fraction less than 1, so this is now exponential decay. Take 2/5 of your previous value. So here's 1. Here's 2/5 of 1, which is 2/5. 40%. 2/5 of 2/5 is 4/25. That's less than a sixth. It's 16%. So yeah, it's shrinking that way. You multiply by 5 halves going the other way, right? Go the other form. 2.5. 2.5 times taller. So 1 times 5 halves is 5 halves. Times another 2.5. I know that that's 6.25, so I'll just go ahead and put that. That's 25 fourths. Times 5 halves is 125 over 16, which is about 9, a little less than 9 something. Wait. Yeah, little... I can't do this. 5, 6, 7. No, it's about 7 something. Hold on. Did I do that right? 5 halves, 25 fourths, 125 sixteenths. Yeah. No, it should be 12 point something. I'm doing something wrong in my head then. 12 or 13 point something. So it keeps going up that direction, right? I don't know what I did wrong in my head. I'm not figuring it out. Oh, 5 halves. I multiplied by 5 fourths, not 5 halves. That's it. 125 over 8. So 125 over 8 would be... Oh, that's probably even taller than that. I don't know. I'll leave it like that. They probably don't do more than that. Okay. That's why the calculator's in use. Okay, so they are using a decimal this time. It's almost... The next 4 are decimals. I'm trying to decide, I'm kind of between whether I should keep in decimal form or convert to a fraction. Because these are pretty clean fractions. I can multiply them and tell you what they become if you'd like to. So y equals 1.2 to the x power. The parentheses here aren't any more required than they are in number 9, but they wrote them, so why not? This is exponential growth, though. It's more than 1. And remember, you are multiplying by 1.2 each time x increases by 1. So 1 times 1.2 is 1.2, and 1.2 times 1.2 is 1.44, so a little less than a half. So you can see this is going to be a very slow increase. 1.2 is also 6/5. So first one is 6/5, and then 36 25ths, and then 216 over 125, which is a little less than 2. And then 1296, not equals, but and then 1296 over 625, which is just more than 2, like that. So it's a very slow increase that way. I'm obviously not going to be calculating more than probably they probably wouldn't fit all those two. And then you take 5/6 and 25 over 36, and then 125. So it's just the reciprocal the other way. It just kind of slowly goes one direction and the other. I don't know if I've been drawing asymptotes each time, but there it is. So not the most beautiful of graphs within here. Maybe this was the wrong time for me to scale these this way. I apologize, but it's something I should get used to using for exponential functions. It seems it'll have its usage time and again. Number 16, y equals 0.75 to the x power. Now 0.75 is also 3/4, so you can see why I'm a little more inclined to use that. Now we did 4/3, that was number 13, so this will just be a reflection of that. I'm going to go a little faster on this one. This is exponential decay. Y-intercept of 1, 3/4 of 1 is 3/4, and then 9/16, a little more than a half. 27 over 64, a little less than a half. And you take 4/3 this way. So 4/3 is 1 1/3, and then 16/9, a little less than 2. And then 64 over 27, more than 2 in some capacity, like that. So you have that takeoff. And It's working it. Do I know the exact decimals? No, you keep multiplying by 0.75, divide by 0.75, and you'll get those values. But those fractions are what you're going for. All right, number 17, y equals 0.6 to the x power. Now, listen, if your teacher, my solution guide videos for my students first and foremost. If your teacher stresses that you use tables, you use tables. And you use a calculator, and you don't round early. You can round for the point, but to get to the next point, you don't round early, or you plug in these values for x, or you use the table feature. All of those are involved, and then you plot the points. I'm giving you something that will give you more structure down the line, depending on how exponential functions are graphed in whatever future we provide, whether it's in the IM2 textbook of Big Ideas Math, or the IM3 textbook in the future, or other worksheet things that I do, or old videos that I have. So all of these would pertain to those, and that's what I'm doing here. Although, suddenly, these weren't as fun to do once I switched over to this graph. I kind of feel bad that I did, because seems a little smaller than my needs tend to be, especially because I'm not using the bottom. I'm sure I have a version of this graph that's just cut off like that, and then I just have the tall portion. I think I'll plan ahead for that in the future. Anyway, 0.6 is also 3/5. This is exponential decay. It's the first time on the left side that we have decay, I think. We take 3/5 of 1, 3/5, and 3/5 of 3/5 is 9/25, so a little more than a third. And, I'm really just roughing it out. I'm really not trying extremely hard to get that what it is. And then 27 over 125, which is a little less than a fifth, or a little more than a fifth, and keeps going. 5/3 is 1 2/3. And then 25/9 is a little less than 3. And then 125 over 27 is a little less than 5. So kind of like that. And we plot and go. Let's get the asymptote drawn. And then the last one on this section, number 18, 1.8 to the x power. Y. Which is also 9/5. This is exponential growth. And starting from 1, we take 9/5 of 1, 1.8. We actually know that number. So we have 1.8 the first time. And then 81 over 25. It's a little more than 3. It's 3 6. Wait a minute. 3 6 25ths. So about 3 1/4. And then 729 over 125, which is a little more than 6, I think. Like 6 point something like that. And then 5/9 this direction. So 5/9, and then 25 over 81, which is a little less than a third, and kind of go in that direction. So maybe it's the wrong time for me to use this kind of graph thing. I'll attach the one with the numbers on the PDF, if that's helpful for you. I don't know. I'm definitely not redoing the video. That's for sure. Okay. So those are those problems. Hopefully a little less graphs in the future that use decimals in that way. There are other ones when we get when we get different a values, I'll be more inclined to do it, because then we're not getting so drastic in what we're multiplying by, because we'll end the window range a lot faster. Okay. Number 19 and 20. We are going to use the graph of f of x equals b to the x to identify the base value, the value of the base b. And I'll tell you straight up, the concept here is, because there are different ways to do this, but the concept is, as we start from 1 here, we go to 3 as x increases by 1. It means you're multiplying by 3. The b value is 3 on number 19. That's all I'm going to kind of provide for you on that. And number 20, the b value goes from 1 to 5, and the b value is 5. That's what you multiply by. The other side, it's 1/5. You're dividing by 5, taking a fifth of that. The b value here is 5. Now, if it went in the decay format, then it would be 1/3 and 1/5, but these ones are not. That's just what those are here. So that's 19 and 20. Number 21, the population of Austin, Texas was about 494,000 at the beginning of a decade. The population increased by about 3% each year. So we are going to be using this y equals a times 1 plus or minus r to the t power formula. If it's increase, we add, and decrease, we subtract. This is an increase in population, so we will be using the plus. So for number 21, we have a as the initial value. That's 494,000. No, I'm sorry, y is in thousands. So a is 494. This is in thousands. The r value, it's an increase of 3%. That means 0.03 will be added to 1. So on part A, they ask you to write a model situating this. This is all in thousands, remember. So this many thousand people equals this many thousand people times 1 plus 0.03 to the t power, or y equals 494 times 1.03 to the t power. That's your model. It's expected to be simplified, use t, and have the proper units, which is in thousands. Part B, estimate when the population was about 590,000. So we have to figure out what value of t, oh, I'm just going to put 590. What value of t will turn this into 590? There are other ways we could talk about doing this, but we can't solve for t straight up, like exactly, without using logarithms. I could divide by 494, but I'm going to go ahead and use the calculator in this fashion, see if you feel comfortable with it, and we'll guess and check and see what the estimate is. I could give you an exact answer too, but it's not the way that we're learning it. So 1 is about 590, so I'm using 494 times 1.03 to some powers. I'm just going to guess something. I'm just going to guess 10. I have no idea what the answer is. But when I do, if I overshoot my value, then I have to try something smaller. And if I undershoot my value, then I have to try something larger. So 3% increase every year for 10 years gives you 663. I overshot. That means it's too large. Let's cut it in half. Let's try 5. 572. A little too small. Let's go up to 6. 589. It looks like it's going to be the 6-year mark. That's really close, 0.86. Even if I tried 6.1, it already overshot it, right? So 6 looks pretty good. What does it say? Estimate when the population was about 590,000. And all I was looking for was the 590. So my estimation is when t is about 6 years. That seems to be the golden ticket of it. So if we get more problems like that, hopefully you recognize what we're going to do for it on estimations. I mean, generally the questions ask you instead, give me the population after 6 years, and then you just plug it in. So it's actually interesting they do it this way. Number 22. You take a 325 milligram dosage of ibuprofen. During each subsequent hour, the amount of medication in your bloodstream decreases by about 29% per year. Each hour, I don't know, I said per year. Each hour, write a decay model giving the amount in milligrams of ibuprofen dosage after the initial dose. Find and interpret the y value when t is 1.5. Okay, so there's where we're going to substitute something after we write the model. So we start with the initial value of 325 milligrams. That's A. The R value is 0.29. However, this one is an exponential decay. It's an exponential decay because it says it decreases 29%. So when I first write this model, it'll be 325 times 1 minus 0.29 raised to the t power. And of course, we should simplify that to 325 times 0.71 to the t power. That's the first part of part A. They also ask you to find and interpret the y value when t equals 1.5. So now we have to do 325 times 0.71 to the 1.5 power. Let me plop that in the calculator. You don't need to bother looking. 325 times 0.71 raised to the 1.5. Okay, I'm getting 194.433406. I don't know how many decimals they want. I'll just put 4. 194.4 milligrams, okay? So the interpretation is after, and remember, this isn't years, this is hours. After 1.5 hours, let's see how they kind of say the language here. There are 194.4 milligrams of ibuprofen in your bloodstream. So that's the interpretation of that. And that's the second part of part A. Part B, estimate how long it takes for you to have 100 milligrams of ibuprofen in your bloodstream. So just like number 21, you're trying to figure out when you get 100 from here by substituting what for t. And this time I'll show you the calculator because we have to check and see how they go. So I just used this before for 1.5. We know it'll be more than 1.5 because as t increases, you get more decay. So let's try 5, and that's 58. That's too large. Let's try 3. That's 116. I want to go up from there. Notice how they used 1 decimal place before. Let's stick to that 1 decimal place. 3.5 was very close. Let's go down to 3.4 and see which one's closer. You can't really tell as far as like, I want to keep going and see how we round. 3.45 versus, let's see, 3.44. 0.04. All right, 3.44 looks closer. So I'm going to round it to 3.4 instead of 3.5. So it really got down to the wire for that one. So after 3.4 hours, 3.44, I mean, it keeps going, right? There's actually even an exact number, which I'm not necessarily providing for you here. But yeah, that T is about 3.4 hours. They don't ask you to interpret that, but that's what it says. After 3.4 hours, you'll have 100 milligrams in your bloodstream. Okay. Number 23. I wonder if 24 is also error analysis. I believe for each problem, for each section, we've always had 2 of them, so that might be on the next page. You invest $500 in the stock of a company. The value of the stock decreases 2% each year. Describe and correct the error in writing... error. Describe and correct the error in writing a model for the value of the stock after t years. So they say initial amount times the decay factor to the t power, and that's where they have a 0.02. So 0.02 is the correct translation, the correct decimal equivalent of 2%. That is correct. The problem is they are using decay factor instead of decay rate. You are supposed to be subtracting 2% from 100%. You take 2% off. They are taking 2% of. They're about to take 2% of 500. You want to take 2% off of 500. So as far as their language, which is it's proper language, but for 23, they are using decay rate instead of decay factor instead of decay rate, where 0.2 should be subtracted from 1. The rest is good model-wise, and I think that's all they're asking after t years. So the correction is y equals 500 times 1 minus 0.02 to the t power, and simplified to 500 times 0.98 to the t power. See, it decreases by 2%. That means after a year, they said, after a year, the stock value will be 98% of what it was, not 2% of what it was. And if it was 2% of what it was, then you have to sell that stock, or you are eating your money. That is going bankrupt. Okay, there is no second error analysis question. We're just on number 24. Okay, this is a recursive rule kind of thing that we're looking at now. Looks like we're doing a lot of these coming up. Complete a table of values from 0 to 5 on n given the recursive rule of an exponential function. So this time they're kind of requiring a table out of me. I will honor the request. And maybe for the first problem, oh, this might be the only one that we do this. N and f of n. Okay, no, I won't do that. I will show you for one step what happens. First of all, they give you the f of 0 is 4. They give you the f of 0 is 4, so we go from there. Now, how do you find 1? Here's the idea of this. Notice the thing that you see to the left, or excuse me, to the right here. F of n equals 3 times f of n minus 1. Here's what it means. I want to find f of 1. I want to find f of 1. So I'm going to take 3. So this is the rule. I'm going to take 3 and multiply it by f of 1 minus 1, or f of 0. Well, we know what f of 0 is. It's 4. So we're going to do 3 times 4. I like to say it the other way, like 4 times 3, which is 12. And that's what f of 1 is, times 3. F of 2 will be 3 times f of 1, 3 times 12, or 12 times 3, which is 36. And then you do 36 times 3, this is how I'm going to do it here on out, is 108. And 108 times 3 is 324. And 324 times 3 is 672. No, 972. So recursive rules may look weird, but what they do is very logical in our heads, especially when you see something like a table with this. The rule may be strange, but the process should be very familiar, especially when you know what it's doing. In 25 to 32, we will write a recursive rule for the exponential function. So number 25, we have y equals 3 times 7 to the x power. So our goal is to basically translate it into this. Let's find out what f of 0 is. And then we will write this f of n equals r times f of n minus 1. And literally, all we're doing is putting in the r and the f of 0. Like, that's it for all these problems. So instead of a blank, let's just put a line here, an underscore. We're trying to figure out those two numbers. And the 3 is the initial value, because when you plug in 0 for x, or n, in some cases, you get 3 out. So that's 3. And the rule is multiplying by 7 each time from one value to the next. 3 times 7, 21 times 7, that number times 7, and it goes forward. And that's the rule, like that. So that's number 25. And these are all the same until, yeah, these are all the same as far as what we do. So these should go pretty fast once you draw the connection of what goes where. And that's not something to memorize. It's something to make sense of why one goes in a certain spot. So for this one here, it's f of 0 equals 25, first term. And then the next term takes requires you take the previous term and multiply by 0.2. So like that. And yeah, that's just the translation for each of these. That's how we roll. Number 27. Y equals 12 times 0.5 to the t power. Doesn't matter if they turn this into an x or into a t. We're using n or the function notation, and all that's good. The initial value is 12, and then the recursive rule is we take 12 initially and then multiply it by 0.5 to get the next term, and then you get half of that, which is 6. Oh, f. Excuse me, f. And then you multiply, you take half of 6 and half of 3 and half of that over and over. Number 28. Y equals 19 times 4 to the t power. This will be f of 0 equals 19. And f of n equals 4 times f of n minus 1. They're saying starting from 19, do that over and over. 4 more of these. If you don't mind, I'm going to proceed a little faster now. I will just write the answer, and I will just replace what I have before. So let me create a template. F of 0 equals f of n equals this times f of n minus 1. So here we go. Number 29, f of 0 equals 0.5. I feel bad that I'm not explaining how these work anymore, but this is just what it is. So that's number 29. It's the multiplier and such. Number 30. Number 30, we replace this with 1/3 and 2. I mean, at this point, at this stage, I don't really know what else to say. Now, if there was more in the exponent, I'd be able to speak on it. Maybe they're prepping you for that, but so far, no. Number 31, we have 4 as the initial and 1/6 as your growth factor. And number 32, we have 0.25. 0.25 is the initial and 2/3 as the growth factor. I want to make sure I wasn't supposed to do anything else for this. No, just write the rule. That would be it. Oh, I'm sorry. These were all different numbers. Those weren't all the 29. As long as you follow the circle, you should be good. Okay, that was 32. Okay, numbers 33 to 36. Show that an exponential model fits the data, then write a recursive rule that models the data. So we still get to do recursive rules. I'm going to leave this here. And let's see what's going on. Let's kind of look at this and check it out. So f of 0 is 0.75. When they say show that a model fits the data, I don't know if they're saying prove that it's an exponential function or write an exponential model like function out of it. I'm not sure, but let's kind of prove that it works. You're multiplying by the same value each and every time that n increases by 1 here. So I think they're just saying just kind of prove its existence. You're multiplying by 2 each time. And if you're uncertain to figure out what you're multiplying by, you can always divide a value by the one before it. 24 divided by 12 is 2. 12 divided by 6 is 2. 6 divided by 3 is 2. 3 divided by 1.5 is 2, and 1.5 divided by 0.75 is 2. Now, all of these will have that, so I don't need to test that each time. I just need to do the division once in case I'm not sure what it is, but this is 2. Now, the two numbers that are important for me here are this one and this one. Although I don't think they're asking for an exponential model, so I don't think I will do this in the future, but this is y equals 0.75 times 2 to the x power. However, they do want a recursive rule, so I'm going to do that, and that is f of 0 is 0.75, and this is f of n equals 2 times f of n minus 1, and that is for number 33. Number 34, and like I said, I probably won't write the model with it as well because we've seen the translation. So number 34, let's just see what the initial is when we look at n equals 0. So that's 2. The initial is 2. And then we are multiplying by what value over and over? It looks like it's 4. You can tell 8 divided by 2 or 32 divided by 8. And maybe you can't tell on the other ones, but they're not trying to trick you. And if they do, I think you'll catch it early. But this is times 4, and that 4 matters for our growth factor. So this is initially 2, and then a 4 that multiplies there. That is the recursive rule. So anyway, when I'm showing this, what I'm showing is that there is that there's a growth factor or a decay factor, that we are multiplying by the same thing over and over from one value to the next as n increases by 1. That's the check. It says show that one fits the data. I don't know if they want an exponential function with it. I really should check on that. Number 35. Now, this one's a little bit different. If you notice on this one here, you might be able to recognize, especially when you get to the smaller numbers, that you're dividing by 2. 12 divided by 2 is 6. 6 divided by 2 is 3. But do I put divided by 2? No, because the r value is not 2. The r value represents what you multiply by. So you have to determine what you're multiplying by, and dividing by 2 is the same as multiplying by 1/2 or 0.5. Either or applies whenever I can do a fraction. It's not a word problem. You'll often see me do that. Now, in case that, again, becomes difficult to figure out what it is, keep in mind what I said. Divide one number by the one before it. 3 over 6 is 1/2. 48 over 96 is 1/2. You divide one by the one before it because we're multiplying by these over and over. Now, the initial value is 96, and you are multiplying by 1/2 from one to the next. So it is still an exponential model that fits the data. Show that an exponential model fits the data. Maybe we do have to write them. I'll just write them right here in case you're like, I need those answers. So let's see. Let's write this as y equals 0.75 times 2 to the x, y equals 2 times 4 to the x, and y equals 96 times 1/2 to the x. Now that's using y and x, not n and f of n. And this is y equals something as well. Okay, so this last one here, you are multiplying. Remember what you're multiplying by. Looks like you're dividing by 3, which means you're multiplying by 1/3. And we start from 162. So there's not much room for me to write what I want to write here. Y equals 162 times 1/3 to the x power, otherwise known as a recursive rule, where 162 is the initial and 1/3 is the decay factor at which that's applied. All right, numbers 37 and 38, we will write an exponential. Yeah, see, I don't think we had to write the function before, but now I think we do. So write an exponential function for the recursive rule. So we're going the other direction. F of 0 is like your a value. So a is 24. In this case, b is 0.1 in the form y equals ab to the x power. So for number 37, this is y equals 24 times 0.1 to the x power, just like that. And this is f of 0 equals 1 half. Number 38, this is 38. Y equals 1 half times, looks like 5 halves to the x power. That's all. All right, number 39. Describe a real-life situation that can be represented by the graph. Write a recursive rule that models the data, then find and interpret f of 6. So this is a graph that's not connected. It has more of that geometric sequence kind of style to it where it's disconnected, right? It's discrete and starts at 0 over and over. So you probably don't want to do something that's very time-wise so much as you want to do something that kind of jumps from one thing to the next, like there's nothing in between, and then it can start at 0, or, there's like there's an initial of something. There's no negatives that we'll refer to. Let's do before I do it, let's explain what's happening. These are scaled by 2s. So it looks like this is 2 and this is 1. This is 1, 2, 4, 8, 16. So your amount is doubling each time. So, okay, so just make sure you know. So I want to come up with a scenario that says every time something happens, another one if something happens, this is doubling. Let's say, and I don't want it to be time. I want it to be an instance of something. For every car wash, you double your... What would double? Like a rumor? Something that goes viral. Okay, here, let's do a video. For every YouTube video that I upload, my subscriber count doubles. Maybe I somehow hit big, which is which not happening here, and I couldn't really care less. But for every YouTube video I upload, my subscriber base. Now, keep in mind, this particular subscriber base starts at 1, like I'm subscribed to myself before a video is made or something, and after one video, it doubles, so I have 2, and then I have 4 and stuff. I only have 16 subscribers after 4 videos, but I hope you realize that when you keep doubling something over and over like that, you go to the millions with a lot faster than you think. A lot faster than you think. That's the first part of it. We have to write a recursive rule still. So the initial value, let's use f of 0. F of 0 was 1, and then this is f of n equals 2 times f of n minus 1. Now they ask you to then find f of 6, and of course to interpret it. Now, if you think about it here, we have f of 4, right? We already have that, and I want to make use of that. F of 4 is 16. To find f of 6, using the recursive rule, we have to know what f of 5 is. I'm going back to kind of the primitive version of this. F of 5 is 2 times f of 4, which is 2 times 16, which is 32. Clearly, you double the previous amount. I'm just giving you how the equation bit works. And then f of 6 is 2 times f of 5, which is 2 times 32, which is 64. So my interpretation, of course, is different from anybody else's because this is open-ended. You can obviously come up with your own or use this, but the interpretation is after 6, well, the first one's the initial. I don't know if that counts as anything. So after I have 64 subscribers after uploading 6 videos to YouTube. All right, so that's the idea for this particular one. See, the initial was initially there. No time has passed. I didn't upload anything yet. At least that's how we're interpreting it. Okay, number 40. The cross-section... How long have we been? Oh, way over an hour. The cross-sectional area of a tree, 4.5 feet from the ground, is called its basal area. I didn't know that. The table shows the basal area... Basal areas in square inches of a tree over time. So year 0, 120... Are these in inch? Wait, hold on. What are they? This is arrows. Square inches. 120 square inches starting in year 0. And then year 1, 132 square inches. Da, 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 da. It keeps moseying along. You can tell as these are exponential. Something's happening here. We want to find out what its multiple. Oh, they tell us. Man, I wanted to show you how to get it. The growth rate is 6%. If you didn't know how, if you had to get that yourself, what would you do? Divide a number by the one before it. 132 over 120, for example. Now, this might not be a perfect value. Actually, that should be. 132. I'm doing this on the calculator. Over 120 is, oh, that's 1.1. So what's this? That's weird. That's not 6% then. Oh, this is tree B. Okay, perfect. So I do have to do something with tree A. So anyway, let me talk about that then. With this table, we got to figure out what we're basically multiplying by from one value to the next there. Times what? Times what are here? So to figure that out, it says write recursive rules that represent the basal areas of the trees, both trees. This one, we have to figure out that model. So 132 over 120 will give us the R value. I have to assume these are rounded values, so I don't want to live off of those ones, but you have to imagine whatever you're multiplying here will work out. Now I divided it and I got 1.1 exactly. That's not even rounded. So 1.1. So there's that. So the growth rate, if you were curious, the growth rate as a decimal, because this other one says 6%, this growth rate is 10%. This is 1 plus 0.1, and 0.1 is 10% decimal equivalent. So there's that, and the initial value, the initial basal area, is 120 square inches. Okay, so what do we want to do? Part A, write recursive rules that represent the basal areas of the trees after t years. Oh, I'm sorry, you couldn't see anything I was writing there. R is 132 over 120, which is 1.1. And then I said that that is a growth rate of 10%. Sorry, I have two different screen things going on here, so it's kind of hard to remember what's where. So part A, write recursive rules that represent for both of them. So for tree A, we have an initial of 120, and then each successive basal area after years, you take 1.1 and multiply by that. Tree B, the initial is 154, and then we multiply by, so what do we multiply by? The growth rate is 6%. 6% growth rate is the same as 1 plus 0.06, which is 1.06. This is what we multiply by here. 1.06 times f of n minus 1. So that's part A. Part B, which tree has a greater initial base area? That would be tree B. B greater initial base. A greater basal area growth rate. That's A. It is 1.1 versus 1.06. A greater basal rate. Use the recursive rules you wrote in part A to justify your answers. Well, I'll say them out loud. The f of 0 is the initial, so that's where b is greater, and this r value within the recursive part is the growth or decay rate that we're referring to. In this case, A, 1.1 is greater. That's my verbal justification. Part C, use a graph to represent the growth of the trees over the interval 0 to 10. Does the graph support your answers in part B? Explain, then make an additional observation from the graph. I'll be honest, I don't know how happy I am to do all that. Because this is going to be... Oof. they're assuming you're going to use a calculator and plug things into a table. Maybe it's time that I do that for the sake of this problem. You can keep multiplying. So you have a few of the values already for tree A. Tree B, you have to get them over and over. I'm going to actually refer to the table in my graphing calculator this time, if you don't mind. And furthermore, yeah, let's see. I'm trying to think of what they would do because they're talking about recursion. They might be asking you just to find the next values using recursion. But if I'm going to use a graphing calculator for it, then I can go ahead and how do I say it? I can go ahead and make an exponential function out of both of these. So I'm going to do just that. Let's go. I have a y equals equation thing I can use, and the first equation has an initial, this is tree A. So 120 times 1.1 to the x power. Where's x? To the x power. And this other one is 154 times 1.06 to the x power. For the sake of this one, actually, I'm not even going to draw the graph. If you're okay with it, I want to show you the table values and then show you the graph. Again, I value my time. I value your time. So if you're going to do it, you keep multiplying your numbers by 1.1 over and over up to 10, and you got to plot them on the graph. And then, oh, and here's the other thing, graph-wise. Hold on. My scale doesn't go to 10. My scales are in the hundreds, so I wouldn't even want to draw the graph this way anyway. I'd want to just kind of makeshift my own. So that's what I'm going to do. I'm going to makeshift one based off the table values that we see and based off the graph that we see. So let's go back to this, and I can look in this table right here. This is when x or t or whatever these is up to 10, from 0 to 10. And I want you to look at these table values with me and what's going on. So what happens is tree A starts smaller as an initial, B is larger. Okay. Now what's going to happen over time with a 10% increase versus 6% increases, this increase will make A go faster. Even though it's less still, you can see how it's climbing the ranks, and by year 6, A is only 6 square inches behind tree B. By year 7, it's probably going to jump it, or at least near it. So year 7, somewhere between 6 and 7, it passed it. It passed it somewhere between 6 and 7, and that's what happened. And then it goes off. It's going, see ya. Now I'm 12 square inches ahead of you, and then 22 square inches ahead, and then 45 or something like that square inches ahead. So it just keeps going from there, obviously. It keeps taking off. Now, as a graph, it goes up into the 300s. So I'm going to go ahead and show you these graphs in kind of a different way. Yeah, up to year 10, that's fine. Okay, so you're going to see two different curves here. So this is tree A as a graph and a model. I'm going to draw this same thing on my thing. And tree B is going to be here as a model over t years or whatever you're doing. So you can see that A passes B between years 6 and 7. So the way that I'm going to draw that is simply like so. I'm going to... What thing did it cross at? I know it's between 6 and 7, but around 200, like 25, something like that mark. So here's 120. And here's, what was the other number? 154. And here's like 230, and here's like 300. Around year 6 to 7, so here's 5, here's 10. So tree A starts at 120, and then that's the one that ends up kind of going higher afterward. So it kind of it's a slow, slight exponential curve up through year 10 where it kind of gets to about there-ish. I mean, it goes forever. No, it says go from 0 to 10. So it goes forever like that, but it will stop at year 10. And then tree B goes from about here, and then it crosses somewhere between year 6 and year 7. That's not very good. And this obviously isn't to scale, but it crosses somewhere between year 6 and year 7, and then it's down below at that time. So that's kind of the idea of these two graphs. Remember, they are curves. They are exponential curves, and they kind of go in that fashion, like that. Not beautiful. That's what I'm going with. Wait, what do we have to do? Does the graph support your answers? Yes. Explain, then make an additional observation from the graph. Another observation. Well, I mentioned it, that tree A is increasing its rate a little more quickly than tree B. Right? I can say that. So it's going to be taking off more and more over time, as tree B is going to lag behind. That they intersect somewhere between year 6 and 7. So those are two observations I can say there. Okay. Let's keep going. In exercises 41 to 44, determine whether the function represents exponential growth or exponential decay. Then identify the percent rate of change. So number 41, we have y equals 5 times 0.6 to the t power. A can be whatever it wants. The growth or decay is based off b, which is between 0 and 1 for this one. So this is exponential decay. Sorry, exponential decay. Now they're asking for the percent rate of change. They're asking how much is changing from 100%. So this percent rate of change, I can call it so check this out. 0.6 is also 1 minus 0.4. And the 0.4 means 40%. This is a 40% decrease. I'll be using the words decrease and increase in these cases. So that's a 40% decrease. That was its percent rate of change. 42. So let's do that same thing for each of these. I have y equals 10 times 1.07 to the t power. This is more than 1. That's exponential growth. This is 1 plus 0.07. 0.07 is 7%. That makes this a 7% increase. Number 43. F of t equals 200 times 4/3 to the t power. Again, the 200 is irrelevant for what they're asking about. Oh, f of t. But the 4/3, and I've stated, I think we had that fraction before. It's more than 1. That makes this exponential growth. And what's the other question? Oh, the increase. Oh, okay. So 4/3, that's like 1.3 repeating. 1.3 repeating. So 1 plus 0.3 repeating means that this guy is like 33.3 repeating percent. Repeating, of course. So that 33.3% growth. Increase. Well, you could say growth, but increase. That is its change. So yes, with that percentage increase, we have to convert that to decimal form in order for that thing to work itself out, and it's that much more than 1. Number 44, f of t equals 0.8 times 1/4 to the t power. This is between 0 and 1. That makes that exponential decay. Box that one, and then this one. And then 1/4 is exactly 0.25. That makes this thing 1 minus 0.75. That makes this thing a 25%. So that makes this thing a 75% decrease. You're taking 3/4 off, taking 75% off of that. Give me a second. Okay, number 45, problem solving. A website recorded the number Y of referrals it received from social media websites over a 10-year period. The results can be modeled by Y equals 2,500 times 1.50 to the t power, where t is the year, and t goes between years 0 and 9. So they restrict our domain over the course of these, 10 years. From 0 to 9 is 10 years, right? No, it's 9. Well, it's 10. That feels like 9. Oh, I guess in the way of like the recursive thing, 0 counts as one of them, 9 is the last one of them. So that's fine. Describe the real-life meaning of 2,500 and 1.50 in the model. So just part A, run 45. It's probably something I have to type out. I don't really know what it is yet. I got to reread this again. A website recorded the number of referrals. So if Y is in referrals, then the initial amount is referrals. So the initial number over a 10-year period. So in year 0, or starting off, initially, initially, the website recorded the number of referrals had 2,500. Whoa. The website had 2,500. Website's not a word. 2,500 referrals from social media websites. I think. I just don't know if I'm spelling websites right suddenly. Oh, and then there's a part B. Or there's a part 2 from this. 1.5. So 1.50 is also 50% increase. The number of referrals is increasing by 50% each year. Okay. Well, that's what that's part B. Okay, so part B, what does the annual percent increase explain? That is this. So 50% increase. I'm trying to think of how to interpret the other part. Describe the real life meaning of, 1.50. You can also say, okay, so here, let me say this then. I'll put this on part B. And then over here, up above, I can say the number of referrals is 1.5 times the previous year. Number of referrals is 1.5 times the previous year's amount. And then that converts to 50% increase. Okay. Yeah, and we're not doing anything with it besides that. Number 46. The population P of a small town after X years can be modeled by the function P equals 6850 times 0.97 to the X power. Let me read the questions first before I start it. I just know I'm going to put A and B. All right. A, what is the annual percent decrease? Explain. B, what is the average rate of change in the population over the first 6 years? Justify your answer. I'll have to think on part B for a second. The annual percent decrease is, so we start from 97%, right? So it's 3% decrease. So 3% decrease. I don't really have much more to say to that. You're taking 3% away from 100%, and there's that. Part B, I don't think I'm going to type anything on this one. I'm going to actually solve it. So the average rate of change in the population, that's a slope. So I'm trying to think of how I want to describe that to you. What we have to do is determine what the population is 6 years later. So we have to do P equals 6850 times 0.97 to the 6th power. This is for 6 years later, and that's going to be about something. I'll just round to the nearest whole number because population is people. It is a small town, and that's what we're doing. So I have 6850 times 0.97 to the 6th power. And that's 5705.8, so I'll say 5706 people. Or population after 6 years. Okay, so here's what we have so far. We have the initial population, and then the population after 6 years. What we have to do is find the average rate of change, how many people on average they lost in between here. Now remember, these graphs, they have a curve to it. That means they lost more in year 1 than they did in year 2, 3, 4, 5, and 6. But the average rate of change will just be this slope right here. So it's not quite accurate as to how they lost the people, right? But, you know, it's like if I double my amount of money every day till I reach $1 million, it's not like I actually averaged like $200,000 a day or whatever, you know? But that's what we're doing here. So the average rate of change, you're going to take the difference, how many people there, 5706, the final, minus 6850 over 6 years. So here, I'm going to calculate that, 5706 minus 6850, and that's negative 1144, dividing that by 6. which is negative 190.6 repeating. So negative 190.7 or negative 191. Let's just keep rounding because we're talking about people. So now I get to type something. What is the average rate of change in the population over the first 6 years? The town is losing an average of 191 people, or the population is decreasing by that many people over the first 6 years. Now that does not continue into future years because you lose less people each year. That's just the natural idea of decay. But that's just what happens over the first 6. All right, number 47 and 48. Justify each step in rewriting the exponential function. Okay, so they rewrote. Let me copy and paste this. I'm going to do both of them. Hey-yo. Oh, I have to say property names. I don't know if I know them. All right, 47. I'll describe what's happening, though. How about that? 47. So here's the original. Oh, yeah, they told write the original function. So here's the original problem. A time. Wait, what are they asking you to do? Okay, just. Okay, this is a rewrite. A times 3 to the t 14th power. Okay, so they are showing you the process for which you could find out what the percent increase or decrease is on a yearly basis or something. They extracted out that t with that 1/14th. That's that power of a power property. Power of power property. And then they evaluate. They do 3 to the 1/14th power. I don't know how to say what's going on there. I guess evaluate rational exponent. I'm not really sure what the name of that step is, but you know they did 3 to the 1/14th power, and then they split this thing right here. So I also don't know what to say for that. Sum, split the sum. I honestly don't know how to describe it. I'll tell you what's going on though, because if we ever have to do another problem like this will help you. If I ever wanted to find out what the percentage increase of this from the thing, it's not 3. Well, here's the thing. It's not 3%. It's not 300%. It's not even 200% because it's not 1 plus 2 because this is not to the t power. You had to get this to its t first and then evaluate what the true b value was and know that it's a 1 plus as it's an increase, and that's the increase. So my words are probably wrong. I think power of power property is pretty good. And I think I can do the same thing for number 48 here. But that's the concept being used. And it's the same thing. So I'm going to copy and paste. The one difference is, which is also in the word, I'm going to split the difference here instead of the sum. So here we're doing the power of power property, getting the t out. We're doing 0.1 to the 1/3 power, which, by the way, remember, means taking the cube root of. You're evaluating the rational exponent, and now we're splitting the difference of 1 and the 0.53. Basically, we obtained the rate of decay, of decreasing. 54% decrease, whatever it is. Okay, probably not the best words. If you want to look at an answer key for it, that's fine. But that's how those can be used. In fact, it looks like this next set is going to ask us to kind of do exactly that. And even these ones. So it looks like what we just did leads you into these. All right, number 49 to 56, rewrite the function to determine whether it represents exponential growth or exponential decay, then identify the percent rate of change. Yes, so that's kind of just what we were looking at before on the previous set. So 49, y equals 0.9 to the t minus 4 power. Now 0.9 would look like decay for you, but whether or not this truly is decay, we still have to make sure we know the proper percent increase or decrease, because this is t minus 4, this isn't t. So t minus 4 power is also the same thing as to the t power over to the 4 power, like that, of 0.9 for each of them. So that splits. I'll show this one time. I showed it on in the lecture portion. I can bring this out in front as this 0.9 is raised to the t power. I guess it's still 0.9. I guess that doesn't change. As long as it's a subtraction, that doesn't change. So this might not be a step which is worth mentioning, but I want to show you that a value that's in front just in case we have to use something with it in the future. So I have to do 1 divided by 0.9 to the 4th power. 1 divided by 0.9 to the 4th power, and that's 1.524. Let's call it 1.52. So here's the ish version of that exponential model, truly, but the b is still 0.9. So this is still exponential decay, and the percent rate of change is a 10% decrease, because that's 90%, which is 10% off. So I'll be straightforward with you on that. Well, you know what? They say rewrite the function. So I guess I still need to do that. But I was going to say, I could skirt not doing some of that stuff, because whenever there's a plus or a minus, it seems like the inside is still going to be the same. And that's probably true. Well, let's go to number 50. Let's do the rewrite. 1.4 to the t plus 8 power. So we'll do the same split. The difference here is that because this is a plus, now this is a multiplication. It's a product. So 1.4 to the 8th power times 1.4 to the t power. And I bring this up first because that's kind of my a value. That's what I want to put first. Now I won't be showing you the calculator. I'm just going to compute this. 1.4 to the 8th power is 14.757. So I'll say 14.76. 14.76 times 1.4 to the t power. So there's the exponential model, kind of in a rounded format. This is more than 1. That makes exponential growth. And 0.4 added from 1, right? 1 plus 0.4 makes that a 40% increase. Okay. Number 51. Y equals 2 times 1.06 to the 9t power. Now this one's not like those other ones in how this is written. This time we have to use the power of a power basis. So this is going to be 2 times 1.06 to the 9th power, and all of that's raised to the t power. Remember, 9 times t, the product, can be split as power of power like this. So let's do 1.06 to the 9th power. This time your b will not actually be 1.06. The a will still be 2. The a is not really relevant to the questions they're asking, but we have to figure out what that is, and I'll tell you. I'm going to round to 2. Yeah, they never do more than 2 decimal places. So I'm going to round to 2 decimal places for this. 1.06 to the 9th power. I'm getting 1.689, so I'm going to call that 1.69 to the t power. It's approximate. This is still exponential growth. And that is a 69% increase. Or 68.947, whatever it is. But a 69% increase. Not 6%. Okay, 52. Y equals 5 times 0.82 to the t fifths power. The same split can be applied. This is 1/5 times t, so I'm going to call that 5 times 0.82 to the 1/5 to the t power. That's also the same as taking the 5th root of 0.82, and this number will actually get closer to 1. When it's a number that's less than 1, it will get closer. It should stay underneath. It should be some percentage decrease. But 0.82 to the 1/5 power is 0.961. I'll just put 0.96. So 5 times 0.96 to the t power. That's exponential decay. And that's a 4% decrease, as that's 96%. X of t. X of t equals 1.45 to the t over 2 power. Very much the same as the last one. where I have, well, there's no a value, but 1.45 to the t to the 1/2, all raised to the t power. I get to take the square root of 1.45. Where's my calculator? Square root of 1.45, and I'm getting 1.204. I'll call that 1.20. X of t is about 1.20 to the t power. So that is exponential growth. And that is a 20% increase. Number 54. I mean, this isn't changing very much. Number 54. We have f of t equals 0.4 times 1.16 to the t minus 1 power. That t minus 1 is also a division. Remember, the 0.4 doesn't apply to this base portion. So 0.4 is still out here. So 0.4 times 1.16 to the t over 1.16 to the first power, over 1.16. Which means now, I mean, it might not have applied to the split, but 0.4 now gets to divide by 1.16, like that, as this is the 1.16 t to the t power. So that guy, even though it's not relevant to the question, I really wish they asked sometimes what's the initial value. And I want to make sure they didn't. I don't think they did. 1.16. So it's 0.3448. So it's about 0.34 times 1.16 to the t. 1.16 is still, I mean, as far as answering the question, this is still exponential growth. It's always been the 1.16 value. But this is exponential growth. Just I had to rewrite the function. And then it's a 16% increase. Okay, numbers 55 and 56. Number 55, we have b of t equals 4 times 0.55 to the t plus 3 power. This is a product of items here, so I have 4 times. So I'll have 0.55 cubed times 0.55 to the t power. So I get to multiply 4 with 0.55 cubed. 4 times 0.55 to the third power for my a, which is 0.6655. And that's actually exact, so I'm going to write that. b of t is exactly 0.6655 times 0.55 to the t power. 0.55 itself didn't change, but this is exponential decay. And what? And 55% is a 45% decrease. I have handwritten typos during these. It's been a lot of writing. Okay, let's go to 56. Where we have r of t equals 0.88 to the 4t power. Now this goes back to the power of a power method. So this is 0.88 to the 4th power, all raised to the t power. That will become an approximation of some sort. 0.88 to the 4th. This is still the b value though. 0.599. So 0.60 to the t power. So r of t, there's the model. That goes back to number 49, right? Wasn't that a 40% decrease? So this is exponential decay and a 40% decrease. Or maybe the other was a 60%. I can't remember. Okay. I forget which problem it was. Okay, let's go. 57 to 62, rewrite the function in the form that or that, so then state the growth or decay rate. So this is more of that, although the a, I don't know how much, okay, the a won't be affected, so I don't really need to, I do need to still calculate something. Okay, let's go. 57, y equals a times 2, rewrite it in the form, times 2 to the t thirds power. Now, this does the same stuff as before. This is a times 2 to the 1/3, and then raised to the t power like that. So we have to take the cube root of 2, 2 to the 1/3 power. So I'm going to be taking 2 to the 1/3, and I'm getting 1.259, so I'll call it 1.26. So a times 1.26 to the t power. Now that's not yet in the form because we have to say what we're adding or subtracting. So that's y equals a times 1 plus 0.26 to the t power. So this does go very much like yeah, hold on, sorry. I'm looking at growth or decay rate. I'm wondering if that's supposed to be a decimal or the percent. I'm going to say the percent. Anyway, what was I saying? This is like those problems that were above where I had to state the reasoning for these. It looks basically just like these ones right here. And that's its purpose. So now we can say what the growth or decay rate of this actually is. It's not 2 or 200% or 100%. It is 26% growth. That is its growth rate. All right, number 58. Y equals a times 0.5 to the t 12ths power, which means we do a times 0.5 to the 1/12th power, all raised to the t power, power of a power. We take 1/12, not 1/12th. We raise 0.5 to the 1/12th. We take the 12th root of that. It's actually going to get pretty close to let's say 0.99. It's 0.943. To my knowledge, did they ever... Oh, you know what? They gave more decimals. I'm going to start doing that. 4 decimal places. Thank you, next. Okay. Let's do that from now on. 4 decimal places. So I have 0.9438... Oh, 0.9439. 0.9439 raised to the t power. So the last one, though, was correct here still because it was 0.2599. So this did still round to that appropriately. So this is a decay, though, right? This is a times 1 minus some value. Now, if you want to figure out what that value is, let me go to the calculator. If you want to figure out what that value is, notice the number that I got through this 0.5 to the 1/12th power. You do 1 minus that to figure out what the other number is. 0.0561. That's what we're subtracting from 1 to get this. And you do 1 minus that to get it, if that makes sense. It's kind of weird. It's kind of backwards. But that's how you figure out the number to get the percent. So it looks like that now. That makes it this much decay. That's 5.61% decay. So that's what we're doing off that. And we might have to do that more and more. And we do, like these next ones are fractions. I want to make the decimal equivalent ultimately. I don't want to round early, but I need to make the decimal equivalent of it to come up with the percentages. So we will do that. Unless this is a perfect, it won't be a perfect fraction. We're good. Y equals a times 2/3 to the t 10ths power. Better rewritten as a to the times 2/3 to the 1/10th power, all raised to the t power. Let's take the 10th root of 2/3. Make sure you put parentheses around that guy if you're going to. Somehow I got a curly brace. 2/3 to the, I'll put 0.1. That's 1/10. And I'm getting 4 decimal places, 0.9603. So y is a times 0.9603 raised to the t power. I can do 1 minus this. It should be 0.0397. Let's check that. 1 minus that. Yeah, 0.0397. So a times 1 minus 0.03. Okay, so there's written in that form. That makes it a 3.97% decay because it was subtraction from 1. We still have 3 more to go on these ones. Okay. Number 60. Y equals A times 5/4 to the t over 22 power. Whew. These numbers are getting big, which means it's going to get closer and closer to 1. This is 1.25 exactly, and then stuff happens. So we're going to have A times 5/4 to the 1 over 22 power, all raised to the t power. So let's do that. So 5 in parentheses, 5/4 raised to the 1 over 22 power. That gives me 1.01019. So I'll say 1.0102. Whoops, hold on. A times 1.0102 raised to the t power. So it's a split. See, the addition ones are always easier. You know that it's whatever number follows 1. So 1 plus 0.0102. Subtraction ones are harder in that way. So this is a 1.02% growth. 2 more. Number 61. Let's move on to another page. Y equals A times 2 to the 8t power. Split that as A times 2 to the 8th power to the t power. Now I think that number is 256. So Y equals 256. Oh, A times 256 to the t power. Wow, that is massive. Now, this is kind of not as easy as it looks for an answer. So that is A times 1 plus 255 to the t power. This is the part where people could get a little confused. Now, I've never seen numbers this big when it comes to how we're perceiving it. Sometimes we just see it as a 3 or whatever, and then people misconstrue what the 3 means. You might even misconstrue what this means. This isn't 255%, it's 25,500%. Because you have to multiply it by 100. You can't just say because it doesn't have decimals that it's not a decimal equivalent of some value, and it is added from 1, and that's what this one is. So I was wondering why that number was coming up. I'm like, these are whole numbers. They look a little cleaner. Well, they actually, they enforced you to do a little bit more, actually. And number 62. Y equals A times 1/3 to the 3t power, which is A times 1/3 cubed to the t power. Now, 1/3 cubed is 1 over 27. So instead of me doing 1/3 cubed, I'm just going to type in the calculator 1 over 27. 0.0370. So A times 0.037. That's good enough. To the t power. Now that's, I'll just do 1 minus. I don't want to think wrong. It's been a minute I've been working on this. 0.963. So Y equals A times 1 minus 0.963. As a reminder, I'm doing 1 minus this number to get that number and write it like 1 minus. So we can now figure out what the percentage decrease is. This guy is a 96.3% decay. You're losing a lot of whatever it was. Whereas the other one, you're gaining a whole lot of whatever it was. All right. Number 63. When a plant or animal dies, it stops acquiring carbon-14 from the atmosphere. The amount Y in grams of carbon-14 in the body of an organism after T years is Y equals A times 0.5 to, oh, it's a half-life question without being called a half-life question. To the T over, its half-life is 5. So, okay, anyway. That model, where A is the initial amount in grams, what percentage of the carbon-14 is released each year? So we kind of have to convert it to that thing, because every 5,730 years, there will be half the amount of carbon-14 in the body than there was before. But we need to figure out after just 1 year. So it's going to be a high number, right? It's going to be, it's going to be a low number, because you'll maintain about 99 something percent, and you'll lose like a percent or less than that. probably a lot less than that. We're going to figure out what that actually is, because it takes 57. Anyway, I'm talking about half-life stuff, and maybe you're less concerned to the t over. But we're doing the same thing as before. We basically got to figure out what b is when there's only a t up here. So we will do a times 0.5 to the 1 over 5730 power, all raised to the t power. So now we're going to do 0.5 raised to that power, basically the 5,730th root of 0.5. 1 over 5730. Okay, take a look at this number, and I'm going to have I'm going to write a few of these numbers here. So 999879. Those look good. To the t power. Okay. And then they say how much is like lost each year. So now I got to do 1 minus that to figure out that value. You know, I don't have to write it in this is what do you call it? Scientific notation. I'll try and convert that for you. 0.0012. No, 0.00012. This looks different from what? 0.00. Yeah, 0.0012. Okay, 0.0012. These other numbers don't look like they match up with 09. Yeah. These numbers don't seem to match up with what that decimal thing shows. So I'm going to stick with 0.0012. That's close enough for me. Okay. Strangely, the calculator seems to be not precise after the other numbers. The other numbers should have said, I don't know. It should have said something different there. Let me try that. Let me try that again. I'm going to use less numbers. 1 minus 0.999879. Okay, 0.121. So 0.0. I'm sorry about this. Just the calculator is doing something really weird. So this is 1 minus 0.00. Hold on, I don't want to get this wrong. Is it 0121? Okay, 0.000121. I think. 1, 2, 3. 1, 2, 3, 4. Yes, okay. Sorry about that. Probably should have paused that part. The scientific notation thing throws me off sometimes. But it still didn't do... Oh, you know what? Maybe it did do it correctly. Okay, anyway. So this helps tell us what the percentage is removed. How do they say it? Is released from the body each year. We got to shift this 2 decimal places over, and it's still 0.0121% released each year. See, you don't want to round to like the nearest tenth, because then the answer is 0%. And you need to say some amount that is there. Okay, anyway. All right, so there's that. Apologies for kind of I'm not really good on scientific notation in the calculator if it doesn't say times 10 to the power. All right, problem solving. The number of duckweed fronds in a pond after T days is this guy, where A is the initial number of fronds. By what percent does the duckweed increase each day? So this is very similar to the last one. Let's hope that we don't have a scientific notation issue. So y equals A times 1230, 0.25 to the t 16th power. I think you know what I'm going to do here. I'm going to be taking the 16th root of 1230.25. So let's do that. 1230.25 versus the 1/16. Oh, wow. Okay, so this, I wonder how significant. I'll probably say 1.56. So take a look at this. 1.55999955. So I guess 1.56 makes the most sense. So A times 1.56 to the t power. Okay. So by what percent after t days. By what percent does the duckweed increase each day? That's 1 plus 0.56, so 56% increase in duckweed each day. Each day. Okay. All right, number 65. A city has a population of 25,000. The population is expected to increase by 5.5% annually for the next decade. Write a function that represents the population y after t years. Okay, so this is the whole y equals a, the initial, 25,000, times, this is an increase, 1 plus 5.5% is 0.055 to the t power. That's each year for the next 10 years it's supposed to do this. So let's simplify that part. That's 1.055 to the t. That is part A. Part B, find the approximate monthly percent increase in population. So now what we're trying to do, let's see, I don't want to do this backwards. Now what you're trying to do is we need to put kind of a 12 up there. Now, see, here t is in years. We want to now put t in months. So if we want to put t in months, we need 12 of those t's to be completed to make a year. I still want to make sure that I'm saying that right. So I think it's supposed to be t over 12, because now t is in months. And then if we work out the stuff that we want to do, it's not 5.5%. We need to do that to the 1/12th power thing on this. And then when we do that, then we'll figure out just how much it increased by each month from that. So that's going to be 25,000 times 1.055 to the 1/12th power, all raised to the t power. And then when we figure that guy out, then we'll get just what that monthly increase was to get to it. So 1.055 to the 1/12th power is 1.00447. I'm going to put 1.0045. So 25,000 times 1.0045 to the t power. Remember, t isn't in years anymore. It's in months. So every month, it's increasing a certain percent. How much? 0.45%. Find the approximate monthly percent. 0.45% increase every month. Now, you might think you would just take 5.5 and divide it by 12. It's not quite how percentages work, though, because it's not linear. 4.5% increase every month grows from the previous amount each time just a little bit. That's why that's necessary. If I just did 5.5 divided by 12, just a heads up, it's going to be close. And I get, well, it's 0.458333. It's really close to it, but we don't divide by 12. We do that conversion the way that you saw before. Okay, in part C, graph the function from part A. Use the graph to estimate the population after 4 years. I'm not going to draw a graph, but I will bring up the one that's on the graphing calculator. This is, I'm past 2 hours, so I'm just going to go to that. So we're going to do, which one do they want? From part A. So 25,000, plus I need to get a good window range here. 1.055 to the x power. This uses an x. And I need my window range to go up quite high here. How do they do this? For the next decade. So I'm going to go for the 10 years. They asked for the next decade. And I need to get in the, I need to make sure in 40,000 that I know what it's looking like. So this goes from 0 to 40,000 on y. Just keep that in mind. Here's 25,000. I might need more than that. I need a little more than that. It goes past 40,000. Let's go to 50,000. Anyway, this is actually exponential. It's not linear, despite its potential. Look, you have to remember, this thing is climbing up very, very slowly over time. Okay, like that. A straight line would go kind of more off like that, and this thing is curving up. Hopefully by the end you can see that. So that's just the drawing. Use the graph to estimate the population after 4 years. I'll happily do that part on here. So looking at the graph, and this window thing isn't perfect on X, notice. I'm trying to get close. It looks like somewhere a little bit around, because it doesn't quite get on X equals 4 for whatever reason. What's right in between there? Looks somewhere around about 30,645. That's my estimate. So around 30,645 people. If you said 30,000, 31,000, you're probably good. All right, number 66. Plutonium-238 is a material that generates steady heat due to decay and is used in power systems for some spacecraft. The function y equals that represents the amount of y, a substance remaining after t years, where a is the initial amount and x is the length of the life of the half-life in years. So I mentioned half-life before. Looks like they say the half-life of plutonium-238 is 88 years, which means it takes 88 years to have half of what you had before. So that's, again, reintroduction to half-life there, only this time they actually say it. So y equals a times 0.5 to the t over x power, and it looks like x will be 88. X equals 88 years. All right, A scientist is studying a 3-gram sample. Write a function that represents the amount y of plutonium-238 after t years. So x is going to be 88 years, and a, the initial, is 3 grams. So the equation we're going to use is y equals 3 times 0.5 to the t over 88 power. That is our model. B, what is the yearly percent decrease of plutonium-238? Now, remember, this is a half-life. T is in years, but 0.5 is after 80. It gets half of it after 88 years. What about just 1 year? So now we have to go to y equals 3 times 0.5 to the 1 over 88th power, all raised to the t power. It's going to be close to that 0.99 kind of stuff. So let's do 0.5 to the 1 over 88. I mean, I like they use real world scenario stuff, though. Like, those are probably real numbers, so we get to actually figure that out. That's pretty cool. So my number is around, I'm going to use 4 decimal places. It's 0.9922. So what is the yearly percent decrease? We have to say it as 1 minus, well, what's 1 minus this number first? I think 0.78, 0.0078, and 2 decimal places over would make it a 0.78% yearly decrease. Okay, part C, graph the function. I'm just going to show you the graph. Graph the function from part A. Use the graph to estimate the amount remaining after 12 years. They do not say sketch a graph, and so there's an interesting distinction. I do believe, maybe I don't remember clearly. I thought they used to say sketch a graph of something if you actually have to sketch it. They're just saying graph it, graphing calculator, whatever. I'm not plugging in numbers over and over recursively for that one. So 3 times, oh wait a second, from part A, 3 times 0.5 to the t, or x in my case, over 88 power. Okay, I am doing that. I think that's the right information. We are within 50,000 isn't going to help us here. What do they want? A 12-year period. So it starts as high as 3, and then it only decreases from there. Remember, it never goes below 0. We're taking half of something after 88 years, and just after 12 years, let's figure out what's going on. So I'll put in 15 just to kind of give a little window range. Let's see the drawing. It's decreasing, and we'll find year 12. I'm going to move this on over. 10, 11, 12. This one's a little closer to 12 here. Let's move this thing up. Remember, this is exponential decay. If I zoomed out more, you would see more of the decay. Looks around 2.7 grams. And that's what I'm going to go ahead and put here. So this graphing calculator isn't quite as accurate as, say, Desmos could be, where you could get kind of the exact answer. I could get you the exact answer using logarithms and such, but that's just an approximation for that. We'll go ahead and move forward. To number 67. Making an argument. Your friend says the graph of f of x equals 2 to the x increases at a faster rate than the graph of g to the x equals 4x when x is greater than 0, greater than or equal to 0. Is your friend correct? Explain your reasoning. I'm copying and pasting this graph here. Okay. Well, I didn't really read what they said. I think this is the line for 4x. Oh, yeah, g of x. Let's graph f of x equals 2 to the x power. That means 1 times 2 to the x power. If these are going by 2's, then this is your 1. And then we double. If you remember how to do this, we double, and 12 and 16 would be way up there somewhere. So let me kind of sketch this graph with it. It's going up that way. Up to 16. Now, your friend says the graph of that increases at a faster rate than the graph of 4x when x is greater than or equal to 0. If they're just talking about the slope, you can tell that there are instances where that's not necessarily true. It's not about it being underneath. That's not what they're talking about. They're not talking about what the y values are. They're talking about the rate of change. And we're not using derivatives here. This isn't calculus. But you can see the instance of the curve here. It's a lesser slope down here. It's a lesser slope here than it is there. Eventually at some point, and I don't know if it's here or what, but eventually at some point they have essentially the same rate of change, and then this one takes off. It needs to take off to pass this line, right? You need to increase at a faster rate there. Oh, I just said increase at a faster rate. But it is accelerating more so because this has a constant rate of change. Increases at a faster rate. So I'll just kind of explain both parts in full here. Although, let's see. So remember, it's not about a height thing. It's about rate of change. So the rate of change of 2 to the x is not always faster. It's not always higher than 4x for all of x is greater than or equal to 0. Greater than, I'm trying to find the symbol. Greater than or equal to 0. However, it very rapidly increases beyond its rate before x equals 4. I don't know specifically where. I'm not really looking into that right now. So before x equals 4, the rate of change itself on 4x is constant, however, whereas the rate of change doubles. No, that's the position. The rate of change is always increasing on 2 to the x. That's kind of as best as I can say. So I'm kind of uncertain whether they're referring to the velocity or the acceleration, if you will, because this thing's always increasing over that time, but its slope, its instantaneous rate of change, isn't quite as large here until probably about there, then it takes off. Okay, that's what I'm going for on that one. I still have 7 problems to go, so let's keep going. Number 68. Consider the graph of an exponential function of the form f of x equals ab to the x. Okay. Determine whether the graph of f represents exponential growth or exponential decay. Well, this is exponential decay. They're not asking to explain, but basically the values are decreasing closer to 0 as time goes on. So it is indeed exponential decay. As x increases, your y values get closer and closer to 0. Part B, what are the domain and range of the function? Explain. Okay, exponential functions have an infinite domain. There is no restriction on x that I can do, and I'm not saying what this equation is, but I can do this to any x power. X can be 1,000, it could be negative 1,000, it can be 1 over 1,000. It can be anything super small, large, negative, whatever it is. So the domain is all real numbers. There are no restrictions on that. The range is a different story, and it's something that I've been mentioning with the asymptote. The asymptote is that way of showing and describing that, we aren't crossing that line ever. The x-axis in this case. This will stay above it because apparently this is taking a quarter of a value over and over, as I can see from 1 to 1/4. If you divide something by 4 over and over, that doesn't make it 0 and it doesn't make it negative. It stays above it. It stays positive. The range is y is greater than 0, not equal to, but greater than 0. And that's what we get for that. That's number 68. Number 69, comparing functions. The two given functions describe the amount y of ibuprofen in milligrams in a person's bloodstream t hours after taking the dosage. So there are two of them. There's 325 times da-da-da and 325 times da-da-da. Show that these models are approximately equivalent to the model you wrote in exercise 22. Okay, let's go to exercise 22. So we wrote 325, sorry, let me first write this. We wrote 325 times, if it's 29% decrease, then I'll say 0.71. 0.71 to the t power. So let's keep that in mind for this problem here. And there are two of them, so we have to do it for both of them. So for, this is problem 69 here. So let's call these A and B, function A and function B. Okay, so for number 69, function A, we have y equals, I'm not going to put the approximate, 325 times 0.9943 to the 60t. We're going to have to raise the Jolly Roger. We're going to have to raise this thing to the 60th power. If you've seen this enough, then you know what's going on there. So let's do 0.9943 to the 60th power. 0.9943 to the 60th power. That number is 0.70965. So I'll put 0.7097 to the t power. Yes, that looks pretty strikingly close to that guy there. So that's model A, function A, whatever you put. Function B is 325 times 0.843 to the 2t. So that would be, we're going to square 0.843. So 0.843 squared is 0.710649 or 0.71. Oh, you know what? This one's exact. 0649. That's pretty close to also that right there. So that's my show on both of those. That, yep, it's pretty close. Is that all they asked you to do? Yes. Describe the information given by each of the models above. Okay, so the initial problem was about a dosage taken every hour. You lose 29% every hour. So you have to keep in mind that T initially was represented in hours. But now you're talking about 60T and 2T. You're talking about what happens after certain numbers of hours now. When you double the number of hours. Wait, no, is that right? No, this is backwards. When it's halfway through the hour and 1/60th of the way through the hour, because now this is represented by the minute, it seems like, right? Is that the right way I'm talking about? Yeah. So this is a minute because you need 60 of those represented to make an hour, and then this is represented by a half hour. So the part B portion of this Describe the information given by each of the models above. So model A refers to the amount, is it lost? Wait, hold on. The amount, I guess remaining in a person's bloodstream. Well, these are all in hours, but the T is the minute, so I want to say this differently. Model A's decay rate is represented by the minute, and Model B's decay rate is represented by the half hour. And again, this is because these are all the same model. In essence, they are, right? The rounding is within the, to the nearest hundredth. They are the same. But giving these here, that 0.9943 means you're losing less than 1% over this time. Remember, over the hour, you lose 29%. Over just a minute, you're losing 0.57%. Over a half hour, you lost 15.7%. But those are just, because this says you need 2 of these half hours to make an hour. You need 60 of these minutes to make an hour. And that's the idea that's being presented there. Okay, number 70, drawing conclusions. The amount A in an account, I know that formula. The amount A in an account after T years with principal P, annual interest rate R, expressed as a decimal, and compounded N times per year is given by this. This is called compounded annual interest, or compounded interest, and it's when you take integrated math 3, this will be very common. You deposit $1,000 into 3 separate bank accounts that each pay 3% annual interest. For each account, evaluate 1 plus R over N to the nth power. Interpret this quantity in the context of the problem, then complete the table. Okay, so I'm going to copy paste the table, and I don't want to give a full lecture on what this stuff is, but you would need to know how to actually do it. The idea of compounding interest, and I've kind of mentioned this before, is that if I do 25% upon 25%, that's not the same thing as 50%. A 25% increase of a 25% increase is slightly more than that, because you're taking 25% increase of not the original the first time, but of 125%. So you get a little bit more. So compounding interest can leave you with a little more money. Not much more. This is not going to be significant in any sort of way. It'll be cents or a couple little dollars here. But it is more. Quarterly, these are the number of times that you compound throughout the year. This has to do with N. N, quarterly, is 4 times throughout the year. Monthly is 12 times throughout the year. And daily is 365 times throughout the year. So there are 3 different accounts. In account number 1, we are going to accrue from a $1,000 principal amount, 1 plus, and they said 3% interest, over 4, this is quarterly, raised to the 4th power. Now, normally it's 4 times T, and T is the number of years, but because this is 1 year, you're only doing this once. And I'm going to round this to 2 decimal places and do it to the nearest cent. That might be significant for these problems. So 1,000 times 1 plus 0.03 over 4 raised to the 4th power. That's just on my calculator. That's $1,030 and about 34 cents. 1,000. Let's do that again. $30 and 34 cents. So that's this guy. 1030.34. Now monthly should get a little more, daily should get a little more. So, not much. And by the way, yearly, let me tell you, and yearly would be $1,030. So 34 cents more for compounding quarterly. Not significant, right? But it depends. This is $1,000. What if it's $1 million? What if you do it after 30 years? There are differences, and that's why you want to pick and choose that interest. 0.03 over 12 raised to the 12th power. So $1,030.42 about. So again, it's just within the same cents. 8 cents more. Does anybody care? No, but it's the overtime thing. It's the what if you had more money invested. And here's the thing, you invest money on top of this investment. So, but this is also why I needed to round to the nearest cent for these. And 365, you might think that, wow, 365 is so much more than 12, that whatever. But you have to remember the concept of, I don't know if the word's diminishing returns or something like that, but, eventually this thing converges. Eventually it becomes insignificant differences and results. So anyway, I'm going to be using 365 here. For some reason I started typing it first. I will write it, don't worry. But I will just say that it is not much more significant. So you might think like, hey, wow, let's do daily because it's so much bigger. I mean, at some point the change is insignificant when it comes to exponents and the like. So 0.03 over 365 to the 365th power, and that number is 1030 point, any guesses? 45. So only 3 cents more than that, which is less of a difference than from quarterly to monthly. In fact, the largest difference would have been from yearly to quarterly. From 1 to 4 would have been 34 cents extra. So there's a big difference. The only other thing I want to mention is that over 4 over 12 over 365 is you got to split up your interest that many times if you're going to do it that many times in the year. Okay, so that's number 70. We have 4 more problems to go. Number 71. Consider the exponential function f of x equals a times b to the x. Show that f of x plus 1 over x equals b. Okay, so I will. But what they are asking you to do is show that when you go from, f of x means y. So the value of y that you get when x is this number. So they're saying, show that when you divide, like on an exponential function graph, show that when you divide this y value by this y value, you basically get the growth factor. You know how we do times 2, times 2, times 2? That this divided by this basically equals 2. That's what they're asking you to do. Even if you didn't know that, we can still do that algebraically. So 71, we have f of x equals a b to the x power. Let's figure out what f of x plus 1 is. That is a b to the x plus 1 power. So f of x plus 1 over f of x is a b to the x plus 1 over a b to the x. Now you don't just cancel things outright like this. However, ab does mean a times b. So a over a can divide and become 1, but this portion here ends up being a subtraction of this over, this over this. So you end up subtracting the exponents, x plus 1 minus x. X minus x is 0, and you're left with b to the first, which is b. So it does indeed show that that should be part A. Part B, use the equation in part A to explain why there is no exponential of the form y equals ab to the x whose graph passes through the points in the table below. Well, the first thing I'll tell you is because there was no change from 0 to 1 here, and then suddenly it does change. In fact, it looks like this changes times 1, then times 2, then times 3, then times 4. Oh, no, that's times 3 again. Then times 3. Let's see what they want us to say. Use the equation in part A to explain why there is no function of the form there. Okay, so let's try one of those. Let's do f of 1 over f of 0. That's going to be 4 over 4, right? The y value when x is 1 and 0, which is 1. And then f of 2 over f of 1 is 8 over 4, which is 2. I mean, you see these numbers. You saw them, what I told you what they were. These are different. Different. It's not a single b value. So there is no thing that can apply if you don't have a constant growth factor. There is no exponential, and then it keeps going, right? The other one's times 3, and then there's a times 3 again. But there is no exponential function that can be applied if the growth factor is not constant. Not constant, which this is not. Now, it does happen to do times 3 twice, so if it did times 3 the whole time, or if that's all that you saw, then that would be true. But we saw a times 1 and a times 2, and it's just not true. All right, number 72, thought-provoking. And for all the times that I've seen thought-provoking, it means open-ended. So we'll see what this means, or at least from what I recall. The function f of x equals b to the x represents an exponential decay function. Write a second exponential decay function in terms of b and x. Yeah, this sounds open-ended. As in, like, come up with something yourself. Oh, I do not want red. All right, number 72. So this is a decay function. So if this is decay, so just remember this. If f of x equals b to the x and it's decay, that means that b is between 0 and 1. What we need is to write another function in terms of b and x so that it remains as decay. And it's open-ended. You can do whatever you want. So it needs to be between 0 and 1. Would 1 over b to the x work? I don't think so. If b was like 1/2, then 1 over b would give you 2. So that doesn't work. You could do 1 minus b. You could do f of x equals 1 minus b to the x power, because if b is 1/2 and you're doing 1 minus 1/2, basically if b is a number less than 1, then you're staying less than 1 still. So this is an example that would work. You could also probably do the other kinds that we've been looking at, like the whole, b, like b to the 2x and stuff like that. Because if I square 1/2, this is b squared to the x. If I square 1/2, it's still between 0 and 1. So this is another example. So you have a couple of examples that you can do. This is, but some of them, they still remain decay in this way. So like this or this, that's very thought-provoking. That actually worked out. But not 1 over b. That wouldn't work. All right, number 73. The number E of eggs a leghorn, I'll say, chicken, a leghorn chicken produces per year can be modeled by this equation, where W is the age in weeks of the chicken and W is greater than or equal to 22. So this model only applies for chickens who are 22 weeks old or older, I guess because that's when they start producing eggs. Part A, identify the decay factor and the percent decrease. So we have E equals 179.2 times 0.89 to the W over 52 power. That's the original part. W has to be greater than or equal to 22. We'll see if that's required for anything we refer to. Identify the decay factor and percent decrease. So W's already in weeks, and over 52 would be throughout the year. So if you wanted annual decay factor, it would be 11% decay. This thing shows you an annual decay, 11%. The chicken can produce 11% less eggs in any future year than they could the year before, whatever that'd be in years. The decay factor they want is likely a weekly decay factor, I'm assuming, because they're talking about the weeks, right? Let's just say this, 11% decay per year, but then let's get a per week one. So per week is, that's too many parts of the E, 179.2 times 0.89, given that this whole section has been doing a bunch of these, and this is the second to last problem, they probably want to make it more challenging, so it's probably like this. So 179.2 times, so 0.89 to the 1 over 52 power. That's 0.99776. I'm going to do 4 decimal places. 0.9978 to the W power. Now 1 minus that number, don't give me it's good. So that's 1 minus 0.0022. Actually, I should have known that. To the W power, which means a 0.22% decrease, decay per week. So per year and per week. Okay, part B. graph the model. I'm just going to show you the graph on here. So 179.2 times, I'll let you see what I see. Whoops. 179.2 times 0.89 raised to the x over 52, in parentheses there. X over 52. Okay, if it starts at 179 and goes downward, and not very much, see, they don't give you a range. It says greater than or equal to 22. So we want to start at 22 and then go later. I'm going to let it stretch out a little bit. Let's see what happens after 100. And, 180 can be my top, and then we'll see what happens as it goes down. So here's a part of the graph of this decay here for the chickadee. So there's the graph. I mean, it's decaying well over time. If I really stretch out the time here, let's go several more weeks. Remember, that's 22 weeks. Let's go to 1,000 weeks and kind of see what happens. So you'll notice more of a curve this time because it starts to get more of that slope off. So there it is. Now, I still need to estimate. It says estimate the egg production of a chicken that is 2.5 years old. They don't say use the graph to do it, so I ain't gonna. So I'm skipping B. You see a version of the graph. This is after 1,000 weeks. So there's that. All right, estimate the egg production of a chicken that is 2.5 years old. Okay, 2.5 years is, well, here's the thing. You can convert it to weeks. You can do 52 times 2.5, but the thing is you really don't need to. So I'll show you what's going to happen. 2.5 times 52 is, I think, 130. Let me check. 2.5 times 52. It's 130. So 130. So now we go to our model, right? E is 179.2 times 0.89 to the 130 over 52 power, right? That's the model. And then you can figure out the egg production of the chicken here. Well, the first thing I'm going to do is 130 over 52. What do you think 130 over 52 is? It's 2.5. So that gets you 2.5 again. So converting it to weeks just to go back to years, if you understand what your model is showing you, that was in years to begin with. This is 11% decrease per year, 2.5 years later. Now let's compute that. But anyway, it's a little redundant to go back and forth that way, basically, because you're back to where you started. Unless you use the week model that I got on that part A thing, and I don't want to because I rounded early with it. So my number that I'm getting, by the way, it's about 133.9, so I'll say 134 eggs per year at 2.5 years old. So that's the production rate that it's doing. That's a lot of eggs, man. I'm glad as an egg eater. Explain how you can rewrite the model so time is measured in years rather than in weeks. It is kind of measured in years, isn't it? Maybe that's what that W thing was for. Hold on a second here. Let me think about this. Explain how you can rewrite the model so that time is measured in years rather than weeks. I suppose, I mean, it is measured in years. Let me think on this one for a second. I mean, I have nothing to think about with this. The only thing is that you just change the W over 52 to like a T, and you just say that, well, okay, now it's in years. The only thing you have to do also is be careful on the domain. So, because this is a yearly amount when W is represented there. That's what the 52 is all about. They're 52 weeks in a year. So on part D, I'll just say you change W over 52 to T, where T is in years. And now the domain is T is greater than or equal to 22 over 52, which can also reduce to, divide those by 2, 11 over 26. I mean, that's just a way of writing the fraction there. That's the domain aspect. So the equation, by the way, would now be E equals 179.2 times 0.89 to the t power. That's the only thing that really comes to mind. This thing is measured in years. If you want the one measured in weeks, then you take this one that I made right here. We used weeks for this, but that's measured in years. Now we use t as a variable for years in this case, I guess, which I kind of did on part C, where I said there was redundancy. All right, the last problem is number 74. You buy a stereo for $1,300 and are able to sell it 4 years later for $275. Assume that the resale value of the stereo decays exponentially with time. Write an equation giving the resale value V in dollars of the stereo as a function of time t in years since you bought it. So you buy a stereo for $1,300. If this is kind of we're talking about decay, it's looking like one of these here. Our A looks like it's $1,300. You sell it 4 years later for $275. So Y is $275 after a t of 4. They're asking to write an equation given the resale value. What we don't have is the percentage of decay. So now we have an equation that can be 275 equals 1,300 times 1 minus r to the 4th power. What we have to do is solve for r in this equation. So it takes a few steps here. We can divide by 1,300 because it multiplies by that stuff here. So 1,300. And I don't think it'll compute perfectly. What I probably will do is leave it like this if it doesn't. 275 over 1,300. No, it doesn't. So I'm going to leave it like that. I could reduce the fraction. Let's see. As a reduced fraction, it's 11 over 52. How about that? 11 over 52 equals 1 minus r to the 4th power. To solve for r, I still have to take the 4th root of these here. Now this is something I'm not going to round. I will leave it as the 4th root of 11 over 52. So 1 minus r equals the 4th root of 11 over 52. I can subtract 1 from both sides and I'll get negative r equals the 4th root 11 over 52 minus 1. Let's see. I probably didn't write this the way I should have written it. Negative 1 plus that. I probably should have left this on the other side. And then divide both sides by negative 1. I get r equals 1 minus the 4th root of 11 over 52. And that looks weird. It's at this point that I will calculate this, and we will get some rounded value that works for us. So the 4th root of 11 over 52, remember, you can use 11 over 52 to the 1/4 power. And as a whole, I'm getting 0.3218. It's 1816318. It keeps going. But that's my r value there. Now, they say write an equation given the resale value as a function of time. So this is the r value. So as a full equation, we can now say the resale value y equals the initial amount 1,300 equals the initial amount 1,300 times 1 minus 0.3218 raised to the t power after t years. And then we clean that up, and we are going to get, I guess I never should have done that 1 minus. 0.6782. 0.6782 raised to the t power. So that should be the resale value there. If I plug 4 into that equation, that's where you should get 275. And then you could do it after 10 years and things like that, and you get the equation from there. So the gist of that problem, once again, was we had to solve for r with the knowledge that we had based on the resale value of this, that it decreases a certain percentage. So we found that. We did it algebraically. Something was multiplied, we divided. Something was raised to a power, we took a root. And then I kind of got weird on the r stuff, but I had to get it by itself, used a final rounded value there, and it works itself out in the decay, and that's the equation. Okay, so that ought to do it for this one, guys. This was a super long one, nearly 3 hours long for the single section. My camera, once again, moved a little bit, but that is the end of Chapter 1. Now, you probably didn't do all 74 problems. You probably didn't even see the end of this video, but thank you so much for watching for what you did. Next would come Chapter 2, I imagine, unless I do any sort of reviews within Chapter 1. Just be ready for anything within. Take care, guys. I will see you in the next one.